Everyone, welcome to the chemistry channel. So today we're going to be talking about ionization energy. And what I want you to do is to imagine an atom. And this atom has a positively charged nucleus and a negatively charged electron. Now the nucleus and the electron are attracted towards each other because they have opposite charges. Opposite charges attract, and this attraction can be described by the Coulombic force, which is equal to K times Q over R squared, where K is a constant, the Q's are the different charges, and R is the distance between them. So this particular interaction, or force of attraction, has a certain energy associated with it. However, this interaction, so this is an interaction, and this is actually called an electrostatic. This electrostatic interaction can actually be overcome if you apply a certain amount of energy to it. So let's just say we happen to apply a certain quantity of energy to it. So this is our energy. And after we apply this energy to it, to the atom, the two species separate. So the nucleus and the electron are now separated by an infinite distance. So this infinity means that they are now separated. So now our atom, so this is our atom, we'll just call this the barrier of our atom, is now positively charged because it lost an electron, and our electron is over here free from the atom. So this is what ionization energy is in a nutshell. Ionization energy is the energy required to break the interaction between an atom and its electron. So it's the energy required to break the interaction between an atom and its electron. And the atom can be neutral or an ion. So ionization energy can be described by a chemical equation. So imagine we have our atom here, and our atom is in the gaseous state. So it's important to note then that ionization energy is measured with atoms in the gaseous state. So our atom is in the gaseous state, and we can symbolize the process of ionization by this chemical equation. So we have our neutral atom on the reactant side, and on the product side we have our cation and our free electron. So this is the process of ionization using a chemical equation. And this form of ionization, this specific chemical equation, is referred to as the first ionization energy. So the energy associated with breaking an electron off a neutral atom is the first ionization energy. So let's write that down. So first ionization energy is the energy associated with breaking the interaction between an electron and a neutral atom. So this is the chemical equation for first ionization energy. However, our definition of ionization energy also applies to ions. So imagine if we take this species here and apply energy to it. So let's take this species, the atom, the cation, and if we apply enough energy to it, we can ionize this species here. And we would form a 2+ cation and another free electron. And this process is called second ionization energy. And this is the energy associated with breaking the interaction between an electron and a positively charged ion. So second ionization energy is the energy associated with breaking the interaction between a +1 cation and its electron. So out of the first and second ionization energy, which do you think will be greater? Which energy amount do you think will be greater? The first ionization energy or the second ionization energy? Hopefully you said that the second ionization energy is larger than the first one. And this should make sense to you. This is because in the second ionization energy, you are breaking an electron off of a positively charged atom. This positively charged atom has a greater pull on the electron, therefore it's much harder to break the electron off the atom. So second ionization energy, so this is second ionization energy, is greater than the first ionization energy. And this is because the positively charged atom has a greater effective nuclear charge than the neutral atom on the electron. So the electron feels a greater charge or a greater pull from the positively charged species than the neutral species. Therefore, it's much harder to pull that electron off because the interaction is so much stronger. So if you were to talk about ionization energy, so let's draw this another atom. So let's just have our positively charged nucleus here, and then we'll write our little positive charge in green. And let's just put our little electron out here. And this electron has a force of attraction acting upon it. And this force of attraction can be described by the Coulombic force, as we talked about. And this interaction has an energy associated with it. So this interaction has an energy associated with it. And if we apply energy to the system, so if we apply energy to the atom, we can break this interaction. So if we apply energy to the atom, we can break this interaction, allowing the two to separate. So ionization energy is endothermic. So the process of ionization is endothermic. So what does endothermic mean? Well, endothermic is another word for taking in heat. So endothermic is a process that takes in heat. So this means heat. So it takes in heat. An endothermic process requires heat in order to run. And this makes sense because heat is just the transfer of energy. So if energy is being transferred into an atom, this energy can be used to break an electron off the atom if the energy is sufficient enough. So therefore, ionization energy is endothermic. And you can sort of think about this when you think about ice, right? So ice in our world, so a block of ice or an ice cube is a solid. And inside this solid, you have molecules interacting with each other. So here we have the water molecule, and each of the molecules interacts with each other. And these interactions, and we're going to talk about these interactions later, are what make ice ice. However, when you apply heat to the system, so energy, when you apply heat to the system, you can break these interactions, allowing ice to melt, forming water. So whenever you have interactions or bonds, you can break them by applying energy. So we can break bonds and interactions by applying or putting in energy. So think about like ripping a piece of paper. It takes ripping cardboard. It takes energy to do that. So the same can be said about the quantum world. So now let's talk about some general trends. So here's our little periodic table. Actually, that's horribly drawn. Let's draw that again. So this is our periodic table, a rough sketch. And we're lucky that ionization energy generally follows the same trend as effective nuclear charge. So ionization energy, in general, follows the same trend as effective nuclear charge. So therefore, as we go from left to right on the periodic table, ionization energy tends to increase. And as we go from bottom to top, ionization energy also tends to increase. However, as we go from right to left, ionization energy decreases. And as we go from top to bottom, ionization energy decreases. And the reasoning behind this is very similar to that we use to describe the behavior and tendencies for the effective nuclear charge. So if you have any questions about effective nuclear charge, please go into the previous video. However, there are some exceptions. So there's two exceptions that you need to know. Sorry about that, my pen's acting a little weird. So there's two exceptions that you need to know. And the first is that beryllium has a higher ionization energy than boron. And this is not what we expect because beryllium is to the left of boron. So why is this the case? So beryllium has the electron configuration of 1s2, 2s2, while boron has the electron configuration of 1s2, 2s2, and 2p1. So the reason why that it's easier to remove an electron from boron than it is to remove an electron from beryllium is due to the fact that we only have one electron in this 2p subshell. And it's a little confusing, but the 2s subshell actually shields the 2p subshell a little bit. So it actually screens the effect of the positive nucleus on the 2p subshell by a little bit. This allows the electron in the 2p subshell to be lost easier than the electron within the 2s subshell. So let's write that down. So because the 2p electron in boron, so this is boron, is screened a little by the 2s electrons. Boron has a lower first ionization energy than beryllium. So there's another exception too. The second exception is nitrogen has a greater ionization energy than oxygen. And we can easily describe this by using our orbital diagrams. So nitrogen has we're only going to focus on the 2p subshell because nitrogen and oxygen only differ by 1 electron. So -1, 0, 1, and this is our 2p subshell. So nitrogen has 5 electrons, and therefore we put there's 3 electrons in the 2p subshell, and oxygen has 4. And you'll notice that we can apply Hund's rule to why the ionization energy of nitrogen is greater than oxygen. Recall that Hund's rule states that when you maximize the spin number in a particular subshell, the energy is the energy of the degenerate orbitals is minimized. So therefore, the energy associated with the 2p subshell in the oxygen is greater than that in the nitrogen. So therefore, in order to lower the energy of oxygen, it's easier to lose this electron and form the maximum spin number than it is to lose the electron in nitrogen and get rid of that maximum spin number. So therefore, oxygen has a lower ionization energy than nitrogen, and it's because of Hund's rule. So this is because of Hund's rule, and you can sort of explain this using Hund's rule. So the last topic that I want to talk about today is writing electron configurations for ions. So the rule for ions is that electrons are always lost from the shells with the highest principal quantum number. So for example, let's use cobalt 3+. So cobalt 3+ has the electron configuration of argon 4s2 3d7. So 3+ means we lose 3 electrons. So using this rule, we take out the 2 electrons in the 4s subshell and then 1 from the 3d. And this would give us the electron configuration of argon 3d6. And that is it for the material for today. So I would like to thank you all for watching, and I hope to see you next time when we talk about electron affinity. So thank you all for watching, and see you next time.